Hello, everyone. My name is Yuying. I am a third-year PhD from Indiana University, Bloomington, and today I'm going to introduce my paper, A Return to Dereverberation in the Frequency Domain using a Joint Learning Approach. So why is dereverberation? Reverberation degrades perceptual speech quality and intelligibility as some reflections of signal structure. The presence of the reverberation may undermine our listening experience. The reverberation could affect many applications, such as the hearing aids, ASR, and the speaker identification. So here's the two spectrograms from clean signal and the reverberant signal. We can see from the reverberant signal on the bottom, the spectrogram, it cannot see clearly as the clean signal. That's why we want to make it look clear as a clean signal and makes it easy for people to listen. For the previous studies, the LSTM predicts the reflections in time frequency domain, and the prediction is subtracted from the reverberant speech signal. And the LSTM can capture time information that could help predicting the late reflections. But it performed on the magnitude, so ignore the phase information, which could affect the results. And the DNN predicts the complex ratio mask, which the mask enhances the magnitude and phase. And the complex ratio mask combines both the magnitude and phase information, but the DNN could not capture the continuous time information. The third study, which is the prediction error, estimates an inverse filter that is subtracted from the reverberated speech. It can handle both the multi-channel and the single-channel situation, and it gives more generalized solution. But it did not perform as well as the DNN approaches. There's another approach that uses the time frequency domain features to predict the dereverberation mask and the ideal ratio mask. It can do source separation and the dereverberation at the same time, but it lack of the time information. So why we want to do frequency domain, not time frequency domain? The dereverberation is often performed in the time frequency domain using mostly deep learning approaches. And time frequency domain processing, however, may not be necessary when reverberation is modeled by the convolution operation. And there's many previous studies performed in the frequency domain, like the ICM, and they require assumptions to hold in different environments, which is not often the case. And a frequency domain deep learning based approach, however, may not need to make these assumptions. So here comes the problem formulation. So for our objective of this paper, we want to remove the late reflections from the corresponding reverberant speech signal by operating in the frequency domain. And we want to predict direct plus early room impulse response in frequency domain. And we propose to use joint LSTM network to predict both the direct plus early room impulse response and late room impulse response in frequency domain. So that we need to know what is reverberation and how the reverberation combine. Reverberant speech signal can be computed as a convolution of a clean speech signal with a room impulse response. And the room impulse response can decompose into direct plus early and plus late. So that's how we define the reverberant signal with the direct sound plus early and the late reflection. Here comes the network architecture of our paper. The input is the time domain, the time signal the reverberant speech in time domain, and we do the FFT. So the input is GFP, and we have three layers of LSTM, and the first part of the output is the late reflections of the late reflection in frequency domain. Then we concatenate the GFP from the first input and the output from the first part together, and concatenate them together as the input of the second part of the network. And we still have like 3 layers of LSTM, and we take the last hidden state from the last hidden layer as our output as the direct plus early room impulse response in frequency domain. Then we do inverse FFT. We can get the direct plus early room impulse response in time domain. For more details, we have 2 different networks. First is the joint LSTM, and the second is joint the FCM, which is the fully connected network. So for the first part, for the LSTM, we have like the number of neurons is set to 2048 for each LSTM layer. And the second part to predict the direct plus early room impulse response in frequency domain. We have the first 2 LSTM layers set the number of neurons to 4096. And the last LSTM layer, we set the number of neurons to 2048. And for the joint FCN network, we have the first part is 3 fully connected layers, and the second part is 3 fully connected layers. And we use the rectified linear activation function throughout the whole 2 different networks. And we use atom optimizer and learning rate 0.0001. And the objective function is the mean square error. For the given features, we're given a time domain reverberancy YP here. We compute the 1024-point discrete Fourier transfer, which is GFP here. Contains the real and imaginary components of the 1024-point GFP as the input. So the first row is imaginary component, and the second row is the real component. And most approaches ignore phase information. And recently, research has shown that including phase information improves the result. And our approach, given the real and imaginary components, means magnitude and phase information are all addressed. Okay, here comes the training labels. We want to predict transfer function of the room impulse response instead of the speech. And the transfer the direct plus early room impulse response and the late room impulse response into 1024-point GFPs as we did for the features, input features, and concatenate the real and imaginary components of the result GFP into one matrix. So that's 2 matrices, one for late reflection and one for direct plus early. And for the objective functions, we train to using the standard backpropagation algorithm with mean square error cost function. And the H hat here is the estimate room impulse response. And the H is the true label of the room impulse response. And we combine both the first part of the network, which is the late reflection prediction, and the second part of the network is the direct plus early room impulse response prediction together as a cost function, and do the backpropagation to update the weight matrix here in the network. And the N is the input dimension, which is 1024 units here. Okay, for the experiment setup, we're using the Timmy corpus as the data set, and randomly select 3,000, 1,000, and 1,000 sentences to construct a training, validation, and testing data set. We simulate the room impulse response from 5 different rooms with image method. The distance between the receiver and the speaker is set to 1 meter in all cases. And we selected 3 different reverberation times, 0.3 seconds, 0.6 seconds, and 0.9 seconds. 1,500 different room impulse response for training set, and 500 different room impulse response for the validation set, and another 500 room impulse responses for testing set. For the evaluation, we convolve the estimated direct plus early room impulse response with King speech. We call it estimated speech, and we compare the estimated speech with the true direct plus early speech signal. And we use 3 different measurements here. The first is the 3 different measurements here: Pascal, Story, and SDR. The Pascal score can range from -0.5 to 4.5, and the Story measure ranges from 0 to 1. And there's no specific range for the SDR measures. And overall, higher values indicate better performance. Okay, here's the result from the table 1 here for our experiments. For the SDR results, the complex ritual mask performs bad as the T6 key equal to 0.3. And the joint LSTM outperforms the comparison approaches as the T6 key increases. For the Story score, the proposed approaches has minor improvements compared with the mixture, but not as good as the complex ritual mask and the ideal ritual mask. For the Pascal score, the proposed approaches outperforms all the baseline approaches here. Overall, our joint learning approaches perform better as T6 key increases, and more noticeable, the results reveal that frequency domain processing often outperforms time frequency domain processing. So we conclude that our approach manages to extract room impulse response frequency information and enhance the reverberant signal. And our approach can enhance the reverberant speech in the complex domain by handling both the real and imaginary information. Our approach deviates from the recent method by processing in the frequency domain. The joint learning method, by adding predicted late information to networks, can help to improve the direct sound plus early reflection that is hard to predict directly. Thank you for your time.